Okay, our next problem is 676. The compound beam is fixed supported at A and supported by rockers at B and C. If there are hinges at D and E, determine the reactions at the supports A, B, and C. Okay, so we are given a system of beams. So first we have beam AD. It is fixed to the wall. Then we have another beam DE. There is a rocker. You can think like this. So there exists a slider at point B. Then we have another beam, third beam, EF. Let's say that this is the F, the free end. And so there is a distributed load. From A to D, the magnitude of the distributed load is 6 kilonewton per meters. From D to B, it is 8 kilonewtons per meters. And from E to F, it is linearly decreasing from 8 kilonewton per meters to 0. There is an external moment, which is 48 kilonewton meters, which is in clockwise direction. The distance from A to D is 2 meters. D to B is 4 meters. From B to E is 2. And from E to C, it is 6. Finally, from C to F, it is 3 meters. Now, first thing that we have to do is to draw the free body diagram of the beams and analyze the problem. Now, first, we will begin with AD. Now, at support A, we have two reaction forces because the beam cannot move in X and Y direction. Certainly, we choose the horizontal coordinate as x-axis and vertical coordinate as y-axis. So I didn't write it, but let me give it here. So this is our choice for the coordinate system. Now, okay, so in x direction, at point A, the object cannot move in x direction, and certainly it cannot move in y direction. Therefore, there is a reaction forces. There are reaction forces. There is a reaction force in x and y direction, respectively, at point A. But moreover, the beam cannot rotate at point A. This basically means that there is something that avoids the rotation. In fact, this is the moment. So we have a reaction moment MA, we have force AX, and we have AY in positive direction. So we choose their direction as positive. Now at point D, the system, if we look at the point D, there is a pin. So it can easily rotate around D. This basically means that there is no reaction moment at point D, but the translation is avoided. So at point the beams cannot move. So we have two reaction forces. In fact, these are dx and dy. Now, second thing is, we have a distributed load which has a magnitude of 6 kilonewton per meters. And remember that it is uniform, constant over the beam, AD. And the resultant force, certainly 6 multiplied by 2, that makes 12 kilonewtons. And in fact, it acts at the center of gravity of the area under the distributed load, so it is just located at the center. So this is basically our free body diagram for the rod AD. Now let's write the equilibrium equations. Of course, sum of the moments with respect to any point is equal to 0. So we write the moment with respect to point A. When we choose the x and y direction like this, certainly z axis is towards us. In order to make it different, in order to avoid the confusion in the notation, so the reaction moment is hereafter will be referred to as MAZ. So we have MAZ, which is positively chosen, plus dy multiplied by 2. Certainly dx will not generate any moment. Since we take the moment with respect to point A, AX and AY will not contribute to the moment equation, moment equilibrium. And we have negative moment generated by the 12 kilonewton resultant force, and that is minus 12 multiplied by 1. And this has to be equal to 0. Now we have here two unknowns, dy and MAZ. Now let's take the moment with respect to point D. Now from here, again, we have MAZ, the moment, reaction moment at point A, minus AY multiplied by 2 plus 12 multiplied by 1, and that's equal to 0. Now the third thing is sum of the moments in x direction has to be equal to 0. We have only two forces, AX and dx in x direction. So AX plus dx is equal to 0. This is our third equation. And sum of the forces in y direction has to be equal to 0. In fact, we have only AY and dy in y direction. So AY plus dy is equal to 12, since the resultant of the distributed load is 12. Okay, so these are the equations. Now we have 4 equations here. Let's go further. Now, next thing is the beam DE. Certainly, action equal to reaction. Therefore, at point D, the direction of the forces has to be reversed. So we have a dx in negative x direction, and we have a dy in negative y direction. If we look at the beam DE, the total length is 6. So the resultant force is 6 multiplied by 8, which makes 38 kilonewtons. We have the support reaction which comes from the B. It is only from direction B in y direction. And we have the reaction forces coming from the beam EF. So we choose their direction as positive. We don't know their direction and magnitude. So EY and EX. So this is the free body diagram of the member DE. Now again, we will write the moment with respect to point D. Therefore, we have this 48 kilonewton force will generate a moment in clockwise direction. As a result, it's minus 48 multiplied by 3 plus by multiplied by 4 plus EY multiplied by 6, and this is equal to 0. And let's say that this is our fifth equation. Now let's take the moment with respect to point E. That will be our next step. So dy will generate a moment in positive direction, dy multiplied by 6 plus 48 multiplied by 3 minus by multiplied by 2, because Vy will generate a moment in the negative direction. That's equal to 0. This is our sixth equation. Now, finally, sum of the forces in x direction has to be equal to 0. From here, I can easily say that dx is equal to ex. This is our seventh equation. And sum of the forces in y direction has to be equal to 0. dy plus ey minus dy minus 48 is equal to 0. This is our eighth equation. Now we have 8 equations, and we have 8 unknowns. Let's continue further. Finally, do we have 8 unknowns? Let's count them. We have ey, ex, 1, 2, 3, 4, 5 here. Okay, and 3 from the other equation. Yes. So 1, 2, 3. Yes. Now 8. Let's continue. We have the member EF. This is our last member. And remember that the peak magnitude is 8 kilonewtons. And sorry, just corrected. This is not 48 kilonewton per meters. The unit has to be kilonewton meters. Okay, let's draw the free body diagram. Again, at point E, action equal to reaction. Therefore, the forces at point E has to be reversed, but should have the same magnitude as the member DE. So it is minus EX minus EY. We have the support reaction that comes from the CY. And then we have the external moment, which is 48 kilonewton meters. The distributed load is linearly decreasing, beginning from the 8 kilonewton per meters. So let's look at the length. So the length of the EF is 9 meters. Okay. So 9 multiplied by 8 divided by 2 gives us the resultant of the distributed load, that is 36 kilonewtons. And certainly it is 3 meters away from the bottom line, so point E. So we have a CY that comes from the support at C. Again, this unit is wrong. This is not 48 kilonewton per meters. It has to be kilonewton meters. Okay, so we have the external moment, 48 kilonewton meters, which is in negative direction. Now let's take the moment with respect to point E. If we take the moment with respect to point E, first the moment we have, which is minus 48. Then CY. CY has a distance of 6 meters, and it will generate a positive moment. CY multiplied by 6. Then the resultant of the distributed load will generate a negative moment. It is minus 36 multiplied by 3, and sum of them has to be equal to 0. Now from here, in this equation, the only unknown is CY. I can easily calculate the CY as 26 kilonewtons. Now, sum of the forces in each direction has to be equal to 0. This tells me something. Since we have only EX in each direction, EX is equal to 0. Now, sum of the forces in Y direction has to be equal to 0. If I look at the forces in Y direction, I have CY in positive direction, minus EY, and minus 36 in Y direction. Now I know the value of CY, so it is 26. From here, I can calculate the EY as minus 10 kilonewtons. Now I know that dx is equal to ex, so dx is again 0. From equation 5, I have 4by, which is equal to 144 minus 6 ey. I know the value of ey, so it is minus 10. From here, this results in 204, and by can be calculated as 51 kilonewtons. From equation 8, I can calculate the dy. dy is equal to by plus ey minus 48. I know the by, it's 51. I know the ey, it's minus 10. Minus 48 will give us minus 7 kilonewtons. Now from equation 3, ax is equal to minus dx. As a result, it is equal to 0. From equation 4, ay is equal to minus 12 minus dy. So remember that dy is equal to minus 7. This gives us 19 kilonewtons. So the support at A do not carry any load in x direction, but in y direction there is a reaction force of 19 kilonewtons. Now from the equation 2, I can easily calculate the reaction moment at point A. That's equal to 2ay minus 12. So ay is equal to 19. And from there, I can say that it is 26 kilonewton per meter in and it is positive, so the direction that we choose is correct for the moment.